All right, hey guys, can I just get a moment of your attention? So episode will be having our exclusively chemistry and biochemistry mix and mingled event next week. So it'll be on February 8th from 4 to 6 in EV Atrium. So you come out, network with professors, and basically grow connections. And there'll also be food platters and drinks provided. Thank you. I'm just gonna leave the mic here. Thank you very much.
Okay. So you all got homeworks, right? Any questions related to homework gradient, please address to TA first. If you won't be able to find the consensus with the TA, let me know. Okay? But the general protocol is you always ask TA first. Then you get to me if you still think that you're right. Okay? So TA can be reached by email, and she will have office hours. The office hours will be posted on Blackboards. I asked today, so she'll probably do that tonight or tomorrow. And so you will be able to meet with gradient TA on a regular basis. Any questions so far? No? Good. All right, so let's proceed then. I just put the reminder what we did last time. So, of course, the big topic was how do we go from time-dependent Schrödinger equation, the most general equation of our course, and the quantum mechanics to time-independent Schrödinger equation. And let me just say that that's possible when our potential part in the Hamiltonian operator doesn't depend on time. Then we can separate, and the total wave function is a product of spatial function, this one, and set some time-dependent exponent. And then, in order to find the spatial function, we need to solve time-independent Schrödinger equation. And that's what we'll be doing for the rest of the semester, solving this problem for different systems, okay, of relevance to, of course, molecular systems. But molecular systems, of course, are too difficult to just address kind of straightforwardly, and we will be looking at them as some models, so with some reduction of complexity. So first, and the most simple problem in quantum mechanics is particle in the box. So the idea here is that we consider only one particle, and that is okay because every molecule consists of electrons and nuclei, right? There are multiple particles, well, at least two types, right? Electrons and nuclei. But in approximation where they do not interact with each other, right? Very crude approximation, then you can consider a single particle in the field of others, right? So that interaction is accounted in a kind of averaged way, where particles that we are not considering at the current point, they are forming the potential for that one particle that we are considering. And many electronic properties of molecules, they are one electron property. So you shine the light, and you may excite the molecule or excite a kind of single electron, or knock the single electron out of the molecule. So that's why particle in the box is, although crude, but very qualitatively important illustration of how the electrons are behaving in the complex objects like molecules. And we will maybe at the end of this lecture consider how this works for polyions, where we have a particular case of quasi one-dimensional system, finite, and that fact that we have a finite system actually will play a big role. So now we start looking at the Hamiltonian. The potential that we are considering is very simple. It's 0 in this range from 0 to L in X, right? and it's infinite outside of that region. So what that makes is it makes confinement of the wave function into the region 2, right, where potential is 0, because if the wave function, say, that we're looking for as a solution of our time-independent Schrödinger equation has anything outside of the region 2, then those parts would be multiplied by infinite potential and will contribute to infinite energy, and we know that that would be a highly energetic solution, which is not important for us because we are interested in finite energies since, well, we're interested in reality, right? So everything what is real has a finite energy. All right, so that kind of limits the way we can present our function that we're looking for. Actually, for those who may not kind of got this part, is that what does that mean to solve this equation is to find the function, right? What does that mean, find function? Well, find the way function depends on the x, on the spatial coordinate, right? So few choices could be x squared, x cubed, sine of x, cosine of x. So like which one of them should form the function, right? So that's the question we are trying to answer. We know the operator, and we know what the result of the operator acting on that function should be. It should be a function times some constant, which is finite, right? And so the result of this problem would be a function and this constant. Once we know function and the constant, actually that is the full solution. Then we can find many properties, like kinetic energy, potential energy, momentum, position, all sorts of properties. Everything will just come out of that solution. All right, so that's why we're looking for the solution. Now this is a differential equation because we have differential operator, kinetic energy. That's kind of a root of all evils because it makes things complicated. It's differentiate our function. Then we have potential, which is quite simple in the region 2. That's where we expect our function to be. Right? It's just 0, so the potential is can be ignored here. And then second derivative of the function is equal to function itself multiplied by a constant. Okay, so that's the equation, and you can already guess what the solution should be because you know functions which if you differentiate you get function back, right? So what are those functions? What are those? Huh? Trigonometry, but yeah, there's a important. It seems like it's an important question. Differentiate once or twice, but I'm saying that it's not that important. Ex, right? So let's say you differentiate it once. What are these functions that when you differentiate them once, you get back the same function, right? So it's the exponent, alpha x, right? Now, if you say, all right, what are the functions that I differentiate twice and I get back the same function? Sine, cosine. Now, what is the relation between sine, cosine, and the exponent? Euler formula. That's why they are actually not that far. Because if you use Euler formula, which was the imaginary, say, exponent, ix equals to cosine of x plus I sine of x. So this formula can be used not just to present weird objects like the exponent of the imaginary numbers, but more importantly, what I like this formula for is to present the sine function, because you can express what the sine function is in terms of the exponents, and it's 1 over 2i exponent of ix minus exponent of minus ix. So essentially you can write sine as just a linear combination of two exponents, and this is very convenient representation when it comes to, say, if someone asks you what is the sine of alpha multiplied by cosine of beta. can you write it down as a sine of alpha plus beta or sine or cosine alpha minus beta? That sort of trigonometry equations which I never managed to remember. So they all can be easily derived if you switch to this representation, because working with exponents is very simple, right? So exponent of alpha times exponent of beta is always exponent of alpha plus beta, unless alpha and beta are operators, but we won't go there. But with numbers, the exponents are multiplicative, and so there is an easy rule how do you kind of combine the exponents. So if you write sine function as linear combination of exponents, cosine function also can be written as 1/2 of the ix plus I minus x, right? So you put the sine and cosine in this expression, and you will get products, linear combination of products of the exponents, and then easily you can obtain the formula which is like kind of products of the sine of alpha plus beta and cosine alpha minus beta, that sort of stuff. So you can do it and obtain these things. Now, as you can see, sine, cosine, or exponent. So exponent is more kind of fundamental. If you can think of this function as a linear combination of exponents, or sine and cosine, because sines and cosines, they appear when you differentiate function twice. They give you back the same function, right? So for simplicity and for kind of consistency with my lecture notes, I'll just assume that we'll be looking for a function here as some coefficient a times cosine. The coefficient doesn't change anything, right? So if you differentiate cosine of some kx, right? And if you differentiate twice the a cosine, then you still get the same result, like in the sense that the function will be again represented essentially. With constant or without constant, the second derivative will be proportional to the function. So you may get some case out of the cosine when you differentiate this function, but the idea is the same. So second derivative will be proportional to the function itself. All right, plus the b of sine. Why do we make this linear combination? Because, well, both cosine and sine are functions which, if you differentiate twice, gives you back the same function, right? So we don't know which one will be the solution. So why not to take both and decide later? So that's the idea. And in math in general, if you have ambiguities, so you are looking for the extra constraint, extra relation that will remove that ambiguity. Otherwise, you must say, okay, this is ambiguous, and I need to put any like if there were any other function like besides cosine and sine that second derivative would give the same would give the function back, then I would add that third function and so on and so forth until I know how to figure out what exactly linear combination should I choose, right? So I don't want to restrict myself to a particular function because that would not be correct, at least at this point, okay? So now let's figure out if we have this, so what will be the result of, let's just make the equation a little bit simpler. And the way we do that is, say, we move the second derivative to the right-hand side, and then it will be, and we divide by, or, right, and we kind of multiply by the inverse of this quantity. All right, so first let's move it, and the equation will be then h squared 2m. Second derivative, I will write the way you wrote it in math class as just a double prime. That's the second derivative. Plus en psi n, that should be 0. And that just comes of me moving this to the right side. So it changes the sign. Then I simplify it further by, say, this is equal to 0, so I can easily multiply the whole thing, left-hand side and right-hand side, by 2m divided by h bar square. So that will achieve that I will really, like, essentially I will have the unit in front of the second derivative, and will have all my constants in the, well, multiplied by the function, right? So I will get to this form. Right, so that's the equation I want to solve. And this part, in order not to repeat it all the time, I'll call k squared. Now you can see that if function n of x is proportional to the cosine of kx, then if I differentiate it twice, that will be proportional to k squared cosine kx, right? With a minus sign. So then, naturally, you can see that if I then consider psi double prime n plus k squared function itself, then I have a chance to get 0, right? Because this is a function, and when I differentiate it twice, derivative of cosine is minus sine, derivative of sine is cosine, so I get minus k squared because every time I differentiate with respect to x, I'm getting k out, right? And plus 1 minus because I go from cosine to sine, right? So then whatever function you choose which is proportional to cosine will be a solution of the equation I'm interested in, right? And then the same thing if I have something that is proportional to sine function. With sine it will be the same logic. Double prime is proportional to minus k squared sine kx. This is just because when we differentiate sine first time, you get k out, but the plus. But when you go from cosine back to sine, the second differentiation, then you get this minus sign, right? So whoever doesn't remember this kind of simple rules that the derivative of the sine is cosine and derivative of the cosine is sine, I suggest just graphically you may remember that the sine at 0 is 0, because that's why sine of x divided by x goes to 1 when x goes to 0, because sine of x is close to 0. So then it's function like that, and then naturally it's a growing function, so the derivative of that function should be positive. And we know that the cosine is going from 1 to lower values, so that function is decaying. That's why cosine derivative is minus sine. Okay, so graphically you can remember that the rule about which one you need to differentiate to get the minus another, and which one will be plus the other. Okay. Anyway, so we differentiate twice, we'll get minus anyway, and so again, then anything proportional to sine will be a solution of this equation, because second derivative gives minus k squared of the function, right? And then we have in this equation k squared plus times function, so they cancel each other and you get 0, right? Very simple. Now both sine and cosine with the k, of course k is an important factor because we have this k squared here in front in the equation. Right, so then both of them are solutions, and all we need to find now is a and b. So how do we do that? Well, this is so-called boundary conditions because they define what the function, what does function look like at the ends of the interval. And so the interval of our interest is 0 to L, right? Now, what we need is the function can be anything inside, but it must be 0 outside, right? So simple consideration of potential energy that it's infinite here, we know that outside of 0L function must be 0. That means if we want function to be continuous, then it must at the ends be 0, right? So there is no way if the function goes like this to the boundary and then starts from, so essentially it approaches 0 from positive side and goes to some finite value a, and then it approaches 0 from the negative side and goes to 0, right? So then there will be discontinuity, which is no good, right? We don't know how to differentiate discontinuous functions. Okay, so that's why the logic is very simple. Function must go to 0 at the boundaries. So we have function n at 0 equals to 0 and function at L equals 0, right? So there are two conditions. Then you have two unknowns, A and B, right? So two conditions and two unknowns. You have a system of equations that you can solve and find A and B, right? So let's see. This condition, x equals 0, function must be 0. As we spoke about the cosine function of x, it's a function which is 1 at 0. So you kind of right away can figure it out that one simple way to make and sine will be 0, right? So sine is 0 at 0. Now if we go with this, what are we going to have? We're going to have a as a function, right? That's pretty much it. So a is the value of the function at 0, right? Everyone follows or everyone doesn't? So you guys, yeah? So you put the 0 here, this will be 0. And you put 0 here, it will be 1. So value of the function at 0 is a, right? Okay, so but value of the function at 0 must be 0. So that means, what does it mean? A is 0, right? So there is no need then to put this term at all. That just follows from the fact that the function must be 0 at boundaries, at least at 1. Okay? And then, what else? So then we are left with this thing to play, right? And, oh, what do we have here? We also need to find, of course, k, because k contains the E of n, and we don't know that. But now there is, there are fewer things to play with. So psi of n at L equals to b times sine, and then here we have a function like k of L, right? And that must be 0. Now, what does this tell us? B is not really a player here because what makes the big difference is this argument, right? So sine function is 0 in a certain values of x, right? So what are those values? What? Say it again, please. Pi x. Why pi x? What is x? X equals pi? Integer. Yeah, okay, but usually we don't use x for the integers. Okay, so it's pi n. How did he figure this out? Well, I would use the circle, magical circle, right? So the sine function is this axis, right? And then it zeros at values of pi, right? So n pi would be, integer of pi would be an argument for the sine function where the sine function is 0, right? So what does this mean? That means in order for the sine kl to be 0, we need kl to be n pi, right? Very simple. What does this mean? Now we know what k is. It's that expression right there. So we can easily make things simpler by just considering that if kl is equal n pi, then k square l square equals n square pi square, right? So it's just more convenient to work with k square, which is already defined. And so then let's just put the k square there. It's en times 2m divided by l, not l, h bar squared, right? So that's our k square multiplied by l square equals to n square pi square. So then simple rearrangement will allow us to get the quantity that is a part of the solution, En. So that's the eigenvalues of the Hamiltonian. Those are the energies. And that's a big deal. So n square pi square h bar square divided by 2m l square, right? So we got energies. With that, we also got what the k should be, because, well, k is related to energy. Okay. So let's just yeah.
Is that so the n has to be an integer, right?
Right.
So is that the reason why the principal quantum number has to be an integer, or because
the principal quantum number? Yeah, it's very similar, because when we will be solving the hydrogen atom problem, right? So the same, like the equation in this form will be the same, exactly the same. It's just for the hydrogen atom, we will need to go beyond one dimension to 3 dimensions. But the idea is the same in the sense that there is this principal quantum number that enumerates the solutions. Okay, and that's going to be an integer number. Okay. All right. So let's then figure out what's this part is, the kx part. So kx equal to, so k is the square root of En multiplied by 2m divided by h bar squared, right? According to this expression with plus minus. So now En is already given. We can work with this. So multiplying by 2m kind of removes 2m from here. Dividing by h bar square removes h bar square, and so what is left is n square pi square divided by l square, all the squared quantities, and so we will get plus minus n pi divided by l.
but there's the x, right?
That's right, there is an x. Okay. Now this plus minus doesn't really make any difference, because we can always put plus minus into the b. Since plus minus in sine function, if it's plus, it's plus. If it's minus, sine minus kx will be equal to minus sine kx, right? So, and the minus will go to the constant. So we always can consider then, because we haven't yet defined what b is, we can write the function as b sine of n pi x divided by L. Do you see anything familiar?
This is how you got the homework. The homework, but also the linear combination expression and the x minus x.
Well,
X minus 3.
it's actually in previous lecture and in homework, what I was giving you as eigenvalues of the kinetic energy operator at the range between 0 and 2 and 0 and 3 were these functions where L was 2 and 3 essentially, right? So they were a solution of the particle in the box, because particle in the box has only kinetic energy in that range between 0 and L and nothing else, because potential is 0. Okay? And I needed the interval so that, there would be finite range to consider. Otherwise, there would be problems with L square integrability. So these functions are more general because L is not specified yet. It can be 0, or it can be 2, 3, or 1, or whatever, 100. So now it's time to find B, right? And the way we find B is from the condition that integral of the psi square dx from 0 to L, because outside of 0 L there is no function. So this should be 1, and then that will give us B square integral of the 0 to L sine of n pi x divided by L dx sine squared right. So this must be 1, and whatever value of this integral is, then taking the inverse of that and taking the square root will give us B, right? Let me just write down the result, which you can find either in lecture notes or by doing this operation yourself. So B is square root of 2 divided by L, and so that's again something that you already saw in the homework. In the lecture, when I was doing L equals 2, there was no prefactor in front of the sine functions. They were already normalized. When you did homework and 2 was substituted by 3 as L, then you should have got the square root of 2 divided by 3 as a normalization factor for all the functions, and it's not n dependent. I mean, no small n dependence of that factor. So again, this is the result that you already saw. Okay. Now let's just combine everything and announce what is the solution of a particle in the box problem, and look at it in details and try to understand what's the physical meaning. Okay, let's see. We specify that ENs are n square, pi square, h bar square, 2ml, and functions square root of 2 divided by L sine and pi x divided by L. Okay, so those are our solutions, and Of course, this is only when x is within the range 0 and L, and function is 0. Let me put a nice bracket. When x is outside the range. Okay. So let's look at the functions first. If we look at the, so this is our, say, range. And then the first function is n equals 1. That's the lowest energy function. As you can see, and the energy of our functions will grow quadratically with n. So n should be 1. Natural question is, why shouldn't we start with n equals 0? What? N equals 0 is 0, yes. So what's the problem? Huh? Yeah, why can't we use n equals 0?
Because the function isn't differentiable in the boundary, but well, there's
0 is differentiable at 0. Like, here's the function, straight line, all values are 0, derivative is 0, second derivative is 0, third derivative is 0, I can differentiate up to infinity. It's infinitely differentiable function. 0 is 0, yeah, so what's the problem? Huh? Energy is 0, not infinity. Look at the wave function. So it's a straight line, right? So, but what are we trying to do here? We're trying to describe particle, right? Particle means, well, there should be probability of its existence between 0 and L, or in the whole space. If we integrate the whole probability density over the whole space, that should be 1. If you have a function where n is 0, sine of 0 is 0, that means there's nothing to consider there. There's no particle. Okay, that's why n0 is not the right choice. It's not the first n that you need to consider, because simply psi squared integral will be 0, and you won't get 1 that you should be getting if you're considering something real, right? So there should be particle to start with if you want to consider particle in the box. Okay. So that's why n equals 1 is the first. And if you plot this function, then you would see something like this. Okay, so it has no nodes, so there is no intersection with the x-axis, right? It only comes to zeros at the boundaries. Other than that, it's like nice, almost like parabola. Actually, if you look at the coefficient of overlap with the function like this, and that's what you probably did for the L equals 3, and I did that for L equals 2 in the lectures, there is a like 90, almost 8 or 9% overlap, so that means Cn squared, where n is 1 for this function, will be close to 98%. So it's really like parabola. Okay, and then when we go to, this is n equals 1, when we go to next n equals 2, then we will start developing nodes. By node, I mean the points in the x-axis where function intersects 0. Okay, so although I'm putting these functions higher and higher in level, but this is my x-axis now, because my kind of 0 level corresponds to growing energy. E1, E2, and so here will be 3. Right? So my notes have nicer pictures of this. But that's kind of the main idea. So if you have the third level, then there will be 2 points of intersection. And you may wonder, why am I focusing on these points of intersection? Well, it turns out that more nodes you have, more intersections you have, the wavier the function is, and the higher the second derivative is. So the kinetic energy, which is the only energy in this problem, right? So this is actually kinetic energy of the function. It will grow with n quadratically. So if you increase, also n corresponds to the number of nodes. So n minus 1 would be the number of nodes. N equals 1 has no nodes, n equals 2 has one node, and so on and so forth. So with number of nodes, your energy will grow. And that is the feature that is coming from the fact that your kinetic energy is a second derivative, and second derivative is bigger when you have objects that are kind of having a higher growth and decay in their relatively small amount of space. And so second derivative is lower when your function is more extended, and it reminds, like the zero kinetic energy would correspond to, of course, straight line, because the second derivative of the line is what? Any line is 0, right? Because line is linear function. You differentiate linear function once, you get a constant. You differentiate twice, you get a 0. Yeah.
So in that case, because you can't have n equal to 0, right? What you included in the initial set for x? Or okay, no, sorry.
So you right? You're referring to this plot, no? No. We're not including n equals 0, right? So we're not including it because it's not a proper function. It just doesn't have a particle. Okay. Okay. Now. Another interesting fact about all these functions, they form stationary states, right? So if you now go back to solution of the time-dependent Schrödinger equation, the solution of the time-dependent Schrödinger equation, let's call it phi, id phi, right, corresponding to any stationary state, as we wrote in the previous lecture, is minus en t divided by h bar psi n, right? So you have a spatial part, and you multiply by this exponent, and that will be the solution of the time-dependent Schrödinger equation. A particular solution, not all solutions, because then you can actually take a linear combination of those solutions, add them with any arbitrary coefficients, and also will be a solution. But the solution that is stationary is like this. So you have a single product of the time exponent and the spatial part. What is interesting is that if you look at the probability density, it will be time independent. So it's so-called standing wave, nothing moves if we look at the probability density. But all the energy that this function has coming from the kinetic energy. So the kinetic energy of all these functions, they are non-zero, they are growing, yet function just develops nodes, but the probability density doesn't move anywhere with time, which is very weird aspect of the quantum mechanics, that we have a kinetic energy, but in classical sense, our particle is not moving anywhere. Okay? Why is that? Well, because simple explanation, kinetic energy is now, in classical mechanics, kinetic energy was mv squared, right? Divided by 2. So you need non-zero velocity. Yeah. Unless you have infinite mass, you need a non-zero velocity, right? So for normal objects with a finite mass, velocity must be non-zero, so that the kinetic energy will be non-zero. Now, in quantum mechanics, kinetic energy is substituted by this operator, and that operator is non-zero, even though there is no kind of velocity velocity hasn't been even defined. Okay, but in this situation, okay, if you are uncomfortable with the undefined velocity, which we can do, but say we can avoid velocity by switching to this expression, right? So it has a momentum, and momentum is defined both in classical and quantum mechanics. So now in the classical mechanics, momentum must be non-zero. So for kinetic energy to be zero, to be non-zero, right? But in quantum mechanics, we have a p squared divided by 2m as a kinetic energy. And it turns out that the average value of the kinetic energy is then average value of the p square operator, and 2m can be taken outside of the averaging procedure. When I say average, what I mean by this expression is, of course, put in some wave function and taking the integral, right? So that's just a short notation. The point here is that for the probability density to move in time, you need to have momentum average to be non-zero, right? But the fact that for all the eigenstates of the particle in the box, we have average momentum equals to 0, that still allows us to have average of p squared to be non-zero. Okay? So, in a sense, to make this more dramatic, you can even write average of the square of the average is 0, but the average of the square is non-zero. I see you are quite excited about this. Right? But with the operators, that's kind of interesting fact, is that average of the operator squared can be really different than average of the operator squared, right? Average of the square of the operator, right? Yeah. So because this is the kinetic energy, it's non-zero, but the momentum itself is 0, and that's why actually momentum is a good quantity to estimate whether the things are moving or not, because you can actually quickly check that any real system, any real function, if you put it in momentum operator, then you get 0, for the simple reason that momentum operator in quantum mechanics is minus h d over dx, right? And then to have average p to be non-zero, then you need a complex function. With the real function, what's going to happen is, imagine you have a real function like particle in the box functions, right? So psi n, they're all real because the sine function is real, right? So now if we take this average, which would be integral over dx from 0 to L, we have psi star n, but it's real, so there is no need to put a star, right? We have minus I h bar d over dx, that's momentum, psi n x dx. Oh, I have over dx here, right? So now minus IH can be taken outside because it's a constant, right? What you have inside is a function which is real and multiplied by derivative of the function which is also real. So product of the function and its derivative always will be real because, well, where do we get the complexity there, right? So the integral will be real. It could be either 0 or non-zero. We don't know yet. But if it's non-zero, the problem with this is that we get minus IH bar in front and then this integral that is something. But we know that average of any quantum observable operator is always real because that's the average of any set of observations we can make, right? But here we have some integral which is real. So this integral is real. times the I, which makes the whole thing complex, unless the integral is 0. Okay, so that's the only way to save the day, right? So you need the 0 integral, otherwise you will get the complex value, and that is going to be disaster. Would be disaster, right? So disaster doesn't happen because the integral is 0. So that means any real function, if you calculate average of the momentum, then it will be just 0. Otherwise, you would get the complex value. The only way to get non-zero momentum is actually to have a complex function. But how do we get the complex functions? Well, you can combine multiple functions like this in linear combinations, then you will get the complex factors from the exponents, and that's why average of the momentum correlates with whether probability density is changing with time or not. Okay. But interestingly, for all stationary states, average of P will be 0, average of P squared is 0, but the kinetic energy is non-zero. So that's just math. Okay? Any questions? So you can just go over the lecture notes, and so it's pretty straightforward, all the stuff that is there. And the next time I guess we'll start looking at the conjugated polyions and how this model helps us to understand their spectrum. Okay.